we're going to talk about projectile motion. And projectile motion is, well, we want to answer this essential question. How do we describe the motion of a projectile moving in 2D space? Now, who remembers what a projectile is? It's an object that's falling, that's true, but now if I'm going to take this eraser, okay, those of you listening at home, I'm going to take this eraser and throw it up in the air. I throw something up in the air, it goes up, it comes down. While it's going up, is it a projectile? Yes. When it stops at the very top, is it a projectile? Yes, but it doesn't stay stopped for more than an instant in time. It starts coming down. So the whole time that it's falling, whether it's going up or down, it is a projectile. And the projectile is an object where the only thing affecting its motion is gravity. Okay? So let me, now we've been dealing with projectiles so far that just go up and come straight down. Okay, that's kind of what we did. But that's kind of boring motion. And so we're going to deal with motion that's a little bit more interesting. Now let me tell you a little story. When I went to Cal Poly San Luis Obispo, hung out with a bunch of my nerdy engineering friends, okay, and there were a bunch of nerdy engineering girls that were standing over here that we knew. They were friends of ours, and we wanted to play a practical joke on them. We were on the other side of the building. Okay. So here we were. Here's me. I'll draw me. Okay. So now, I didn't have a beard back then, but we could draw. Now, we got some surgical tubing. We got an old sock, and we cut it up, and we got some water balloons. And we would pull that sucker back all the way to the ground, and then we would launch it. And that water balloon would have an initial velocity, which was fast. We had a really good water balloon launcher. And we would have to tilt it at a certain angle. We call this the launch angle, that angle theta. And we were hoping the balloon would go up and over the building and hit the intended target. We'll teach them for ignoring us. Okay. Now, and here's how it worked. We had a friend who lived on the top floor. Here's a hallway. Here's a cross-section of the building. There's a hallway. There's a dorm room here, dorm room here. These are the red brick dorms. I think it was like Sequoia Hall or something at Cal Poly. And we had a buddy who lived on the top floor. So what he would do is that he was up here in this room, and he would look and see where we are. And then we would launch the balloon, and he would run across the hall. And, and then look down this way through this window and see where the balloon came down. Smack, right here, okay? And then he would run back to the other side, and he would say, less angle. So we would have a little less angle, and so that would change the trajectory, and so we kept missing. I think we shot about 4 or 5 of them. Until the last one. He said less angle because so we did less angle, and something unfortunate happened. His window was open, and there was a screen, and we shot that water balloon, and it hit right in the middle of the screen. It was awesome. I'm so glad this was not my room, because when the water balloon hit the screen basically divided up all the water in the water balloon into trillions of little water droplets and completely covered his room. It was like somebody took a spray bottle and sprayed everything in his room. It was homework, books, everything. I mean, it was just one water balloon, but it was evenly spread out through his entire room. It was incredible. We never did hit those girls, though. Oh well, I eventually found one that paid attention to me. All right.
Did you hit her with a water balloon?
No. That's why Evan exists today. Now, so we want to understand this kind of motion. I want to be able to throw something in the air. Now, notice something that really you can think of this water balloon as doing two things at once. The water balloon is moving horizontally, like this, while it's also at the same time going up and down at the same time. And so what we're going to have to do to understand this motion is kind of look at the balloon. Let me redraw the path of the balloon, the water balloon. Here's the ground, a level, nice level ground. We'll get rid of the building. Now you know what kind of makes this path. Remember when we did the having a ball ladder? You guys have thrown stuff around. It makes this kind of this parabola-looking shape. Now, if you look at the balloon at various places in this, on this trajectory, and here it is just before it hits the ground. Well, we've got this initial velocity, and we've got this angle, which means the balloon is moving in the x direction, that is the horizontal direction, we're going to call it the x direction, and the vertical direction at the same time. Does that make sense? So the first thing we need to do is define the x direction and the y direction. And this is how we're going to define it for all these problems. Now let's look at the balloon. The instant this balloon is released, and let's say it's released essentially from ground level. Well, this initial velocity can be broken up into its components, like we talked about with vectors. It is a vector. And actually, if I give you the speed, the velocity of the balloon and this angle, what have I given you? I've given you the velocity vector in blank coordinates. What goes in the blank? Polar coordinates. All right, so one of the things we're going to need to do is take that initial velocity and say, well, this is the initial velocity in the x direction, and this is the initial velocity in the y direction. Yes? Okay. And notice that the initial velocity, the total initial velocity, is the hypotenuse of a right triangle that is composed of components of v naught x, v naught y, and this is going to be v naught times what? V naught times, what am I going to fill in there? This is going to be v naught times, what am I going to put there? If you're listening at home, you can try it yourself.
Cosine v naught y.
V naught y thing. No, v naught. V naught y is v naught
Sine theta.
sine theta, yay! And this is v naught cosine theta. See, that's how I get the components, the x and y components of the initial velocity. Now, we are going to do this. Ignore air resistance. Air resistance is futile. Because if we were to include air resistance in our analysis, that analysis would be extremely complicated. That is like junior, senior level mechanical or aeronautical engineering. And we must walk before we can run. So we are going to make the simplifying assumption that air resistance is negligible. And for slow speeds, it is negligible. Even for this water balloon, the effect of air resistance would make maybe a difference of maybe a half a meter in where it would land. It's not that big a deal. So now if you're throwing a wiffle ball, or a ping pong ball as hard as you can, the air resistance is not futile, it is significant, and so you will need to include it in your analysis, but we're going to ignore it for now. Now, if that's true, imagine this water balloon everywhere. What's the only thing interacting with it? What's the only thing affecting its motion? Gravity, right? So the acceleration is what? The acceleration on the water balloon is equal to negative 9.8 meters per second squared in the y direction. Y direction. So the acceleration in the y direction, a sub y, I'll call this subscript y to indicate the direction that acceleration is in, is equal to negative 9.8 meters per second squared. Now, because we are ignoring air resistance, there is nothing interacting with the water balloon in the horizontal or in the x direction. So what's the acceleration in the x direction once it's left the slingshot? There is none. There is nothing interacting with it horizontally. There's no air resistance. We're neglecting air resistance. So therefore, the acceleration in the x direction is 0. So the acceleration in the x direction is 0. So if I were to draw the... now, what does that mean? Acceleration in the x direction is 0. What does that mean is true about the velocity in the x direction? If there's no acceleration, what's true about the velocity? It is a constant. That's right. Which means no matter if you look at the horizontal velocity, horizontal velocity, horizontal velocity, horizontal velocity, horizontal velocity, horizontal velocity, everywhere along that path, that trajectory, the horizontal velocity of the ball or of the water balloon is a constant. It is, in fact, well, I'll do it here, v naught x. And v naught x is v naught cosine theta. So the velocity in the x direction is a constant from the time it leaves the slingshot until just before it hits the ground. Yes? Okay. But what is the acceleration in the y direction? Negative 9.8 the whole time. So if you were to draw the velocity vector in the y direction, well, here's the velocity in the y direction. Now here's the velocity in the y direction. Now it's 0. Here's the velocity in the y direction. Here's the velocity in the y direction. So the velocity in the y direction is getting smaller and then bigger. Smaller up, bigger down. Okay? There's read the book. There's a really good diagram in the book showing it better than I drew it right here. Well, this means since the acceleration is a constant, what does that mean we can use? If acceleration is constant, we can use the, what did we study last unit? The, starts with a K, kinematic equations. That's right. So now we're going to apply the kinematic equations to this situation. But we're going to apply it in the x direction and the y direction. If you're looking at the, well, let me just start over here. New sheet of paper. In the x direction, well, let's just write all the kinematic equations, all 4 of them, right? But I'm going to put a subscript x for everything. So we have Vx, the final velocity in the x equals v naught x plus the acceleration in the x times time. Then we have delta x equals v naught x plus vx over 2 times time. That's the second kinematic equation. And then we have the third kinematic equation. Delta x equals v naught x times time plus 1/2 the acceleration in the x direction times time squared. And then we have the final velocity in the x direction squared plus the initial velocity in the x direction squared plus twice the acceleration in the x direction times our displacement in the x direction. But what did we say is true about the acceleration in the x direction? It is 0. So let's take all of these and make the acceleration 0. That's 0. This goes away, and this goes away. Well, let's take a look at what happens here. The first kinematic equation just says, hey, my final velocity is equal to my initial velocity in the x direction. Because what's true about the velocity in the x direction? It is constant, yes. Well, let's do this one. Let's do the third kinematic equation. It says delta x equals v naught x times t. Now this implies that the acceleration in the x direction, I'm recording right now. This implies that the velocity is a constant. Remember that constant velocity model we did in Unit 1? The buggy car moving along the floor? Okay? Now, the other two just reduce to this. Look at this one. Well, if the velocity in the initial velocity in the x direction is equal to the velocity in the x direction, if these two are equal, well, I can say, look, this is equal to that. So really what I have here is v naught x plus v naught x, right? This is equal to v naught x. Well, what's v naught x plus v naught x? 2v naught x. What is 2v naught x divided by 2? V naught x. And you get delta x equals v naught x times t. So this equation and this equation give us the same result. Give us this. And then look at this one. What does this say? V naught x squared, vx squared equals v naught x squared. Take square root of both sides and you get this. So these two equations give us this. These two equations give us this. So really, in the x direction, these are the only two kinematic equations that we really need to use. Are you with me? Okay. Just putting a guilt trip on. Don't cry. All right. If anybody needs a shoulder hug. Have a chocolate. All right. Now we're going to look at the y direction. We're going to do the same thing. The final velocity in the y direction equals the initial velocity in the y direction plus the acceleration in the y direction times time. Delta y equals v naught y plus vy over 2 times time. Delta y equals v naught y times t plus 1/2 ay times t squared. And vy squared equals v naught y squared plus 2a in the y times delta y. Those are the four kinematic equations. And we need them all. We can use them all. Because we do know. But what do we know is true about the acceleration? Acceleration in the y direction is negative 9.8 meters per second squared, at least if we're throwing a ball on the Earth. If you're on the moon, if you're on Mars, it's different. Are you really that cold? Okay. All right, now, there is a couple other things you need to know. V naught x equals v naught cosine theta. This is the total initial velocity. This is the launch angle. And v naught y equals v naught times the sine of the angle. Okay, but if you're looking at the x direction stuff and the y direction stuff, what's the same? What is the link between your motion in the x direction and your motion in the y direction? The link between them is that the motion in the x and the motion in the y are happening at the same time. Well, let's put them here and here and here. They're happening at the same time. So what this means is that if you're looking at a projectile moving in 2 dimensions, you can isolate its motion in the x direction and use this equation right here and solve for time. And then you can use that time to solve your motion in the y direction. Time is the link. Or you can do the opposite. You can look in the y direction, solve for time using one of these. Now you can't use the fourth kinematic equation to do this, but you can use the first three because they all have time in it. Solve these for time and then use that time in the x direction. You can use that to figure out what your initial velocity in the x direction was or what your delta x is, depending on what's given in the problem. Make sense? Now let me show you the 2 basic types of problems that you're going to have to solve for projectile motion problems. And there will be a couple of more that are a little more difficult, but I'm going to save those for later. Lucky you. Okay, first kind of problem is the cliff problem. The cliff problem. So here's the top of a cliff. Okay, so here's, now this also, sometimes it's a building, like you're throwing something out of a window in a building, or off the roof of a building, or you're kicking a stone off the top of a cliff. Or it could even be an airplane where you drop something out of an airplane. They all work this way. Suppose you have like an object and its initial velocity is horizontal, like this. Now, if this is the initial velocity, what's the launch angle if I throw it horizontally? 0. And so if you go, okay, v naught x equals v naught cosine theta, well, v naught, what cosine theta, what's the cosine of 0? 1. So really, look, v naught here is v naught x. I think you can see that. Okay. So if I say you throw a rock off of a cliff, but you throw it horizontally with a velocity of 15 meters per second, well, if you throw it initially like that, well, then your total initial velocity, that is the velocity in the x direction. So if this is true, then what's the initial velocity in the y direction? What do you think? If you throw something horizontally, as soon as it leaves your hand, what is its velocity in the y direction? 0. That's useful information. And then the rock's going to go smack. Notice that this is like half a parabola. Well, we have a delta y, don't we? Now notice that this delta y is going to be negative, right? Because the stone, or whatever the object is falling down, and we said that down is negative. So delta y will be a negative value. Watch for that. We also know what the acceleration in the y direction is. It's negative 9.8 meters per second squared. We also know that the acceleration in the x direction is 0. We're going to assume that's always true. And when you have a problem, you have to identify your x and y direction. And now, this is all the stuff that's given. And then this is delta x. This is your displacement in the x direction. And they usually mean from the base of the cliff out to where it hits the ground. That's your delta x. Well, you now have, for this kind of problem, you have these equations to use. Let me zoom out for a minute. So you can apply all of these to this, depending on what you're given, depending on what you're trying to find. So these right here, all the stuff that I just wrote right here, you should put that on your equation list. Right now, I mean, before you do your homework. And then you need to draw a picture of the problem, look at what's given, look at what you're trying to find, and then apply these. Now, I guarantee you, for example, if you need to find delta x, they will give you delta y. And you will be able to use delta y to figure out how much time it took for that stone to hit the ground. If you know that and you know the initial velocity, you can figure out how far that rock is going to go before it hits the ground. Or they could be they could give you how far it went and how fast you threw it and figure out how high the cliff is. I mean, there's a wide variety of what they can give you and what you're trying to find, but they'll all be set up this way. So that's the cliff problem. The other major type of problem that you'll get with projectile motion is, and I call it the kickoff problem, like in football. Of course, it doesn't have to be a football. It could be an archer shooting an arrow. It could be somebody throwing a baseball or anything like that. But here's the basic assumption that we make. The reason I call it a kickoff problem, here's a level ground. And here's the football, and you kick the ball off the ground, and it has some initial velocity and some launch angle. This is like what we started with. And it goes up and down. Okay. Now there are things that we know here. So if you get a kickoff problem, sketch it. Write down what's given, draw the sketch. You know this, you probably know the angle. Now this, V naught x equals V naught cosine theta, V naught sine theta. Of course you know that. Now let's look at the very top. Tell me what's true about the velocity at the very top. Is the velocity 0 at the very top? Excellent. Yes, the velocity in the y direction is 0 at the very top. But what is the velocity in the x direction? It's this. It's constant, right? It's V naught cosine theta. This is V naught cosine. Everywhere in the trajectory, after it's kicked and before it hits the ground, the velocity in the x direction is a constant. Here's another thing. Let's say you want to know how much time it takes to go from up here all the way back to the ground. The full thing. Well, what's true about delta y when it hits the ground? Yeah. Delta y is equal to 0 if it starts from the ground and ends at the ground, and the ground is level, you're not on a hill, then delta y is equal to 0. So sometimes they won't tell you that, right? They won't tell you in the book. They'll just tell you that it goes up and down and what's the hang time. Or they give you the hang time and they want you to find like delta x, what was the range? Or what was the maximum height? Now, the maximum height there is happens obviously when the velocity in the y direction is 0. So you can use these facts, that delta y is 0 for the whole thing, as well as, you know, these equations here to solve the problem. And you're almost always going to look in the y direction and deal with time and then use that time in the x direction. Or you're going to do the opposite. You're going to look in the x direction, find time, and then use that time in the y direction. Okay? There's some other little tricks to solving projectile motion problems, but I think what you need to do is practice them, and then the little subtle tricks. Like here's a subtle little trick. The time it takes to go up is the same as the time it takes to come down if you have a kickoff problem. And once you know that fact, you can figure out, like if I don't give you the initial velocity but I give you the time, you can use that to solve. There's all kinds of ways of doing these problems. Okay, so it's really really projectile motion problems is very much solving the kind of problems that we've solved before in Unit 1, where we're dealing with constant velocity motion. Now that's just the horizontal component of the motion, is constant velocity, and we dealt with constant acceleration motion, but now that's the y component of the motion of the projectile, and now we have to link those two together because they are happening at the same time for a moving projectile. Okay? And that's how we describe the motion of a projectile in two-dimensional space, in a plane. Okay, we're not going to deal with three-dimensional crazy motion in here. This is crazy enough. Okay, any questions? Okay. That is all.